Have you ever felt like infinity is, well, kind of just a cop-out? Like it's a mathematical rug we sweep our toughest paradoxes under. Welcome to this explainer. Today, we're going to completely challenge your foundational understanding of geometric reality. We're talking about reframing Zeno's famous paradox, completely ditching Descartes' legacy, and fixing those infinite loops that constantly plague our understanding of space and computation. Let's get into it.
Here's our roadmap for this journey. First, we'll tackle the zero-dimensional problem. Then, we'll look at Achilles, the tortoise, and a squirrel. After that, we'll cover the discrete tiled surface, move on to grounding the silver ratio, and finally, we'll talk about halting the infinite loop. Okay, let's dive into part 1, the zero-dimensional problem.
To understand the geometric fix we're exploring today, we really have to ask a pretty bold question. Is infinity actually just a bug in our foundational math? Because, for centuries we've relied on the traditional Cartesian, continuous point set manifold, which is really just a fancy way of saying we map reality using an x and y axis, plotting coordinate points that have exactly 0 dimensions. They're infinitely small. But here's the massive issue with that. Those zero-dimensional infinitesimal locations create what the source material calls a ghost grid. Since these points have absolutely no physical surface area, you can theoretically divide them forever and ever. And this leads to something called Naperian drift. This is where coordinates literally lose their physical reference, logic entirely breaks down, and we end up just chasing vanishing points into an endless void.
So let's compare the old paradigm with this new one. On the left here, we've got Descartes' zero-dimensional points. This model assumes infinite division on that ghost grid, which inadvertently takes the irrationality of Turing's halting incompleteness and Zeno's paradoxes and treats them as actual proof of perpetuities. It basically creates mathematical problems it simply cannot solve. But then, on the right, we have the proposed solution, discrete tiled surfaces. You'll sometimes hear this called the Gunky manifold. In this framework, geometry is built on finite, discrete areas, not those dimensionless points. It actually provides a physical halting boundary and uses what are described as Turing-complete metabolic cells to give information some genuine stability. Moving right along to section 2, Achilles, tortoise, and squirrel. To make all this abstract math a little easier to picture, we've got this absolutely surreal visual metaphor. You can see the classic Greek hero Achilles riding the tortoise. Now, historically, Zeno's paradox argued that Achilles could never actually catch the tortoise because the distance between them could just be infinitely halved over and over again. But look closely at what they're actually moving over here. Those are nested log cabin-style spiral cells. And these cells represent base scale resolution in our new discrete manifold. So the path they're on isn't some infinitely divisible abstract line. It's actually made of discrete physical tiles. Now, what's really interesting about this image is that character floating on the right. Yep, that is a flying squirrel, and it's riding a giant cork stopper labeled with the letter D. In this framework, D stands for the finite area end. This cork is literally the physical boundary that formally halts the infinite loop of the paradox. So instead of Achilles just infinitely shrinking down into a zero-dimensional vanishing point, he eventually just hits the cork. The geometric regression stops entirely because it hits a foundational surface primitive that physically cannot be divided any further. Boom, paradox solved. Which brings us to section 3, the discrete tiled surface. So how does this actually work under the hood? Well, it all starts with defining the base scale. Instead of an abstract, infinitesimal origin point just floating out there in nothingness, this geometry uses a foundational 1-to-1 ratio cell. It's defined by the equation D equals C minus B over A. But more importantly, it beautifully utilizes Thales' theorem, the incredibly familiar A squared plus B squared equals C squared, to ground the geometry in actual physical reality. By using spiral cells to handle nestings and loops, it makes sure that all calculations resolve at a finite area, D, which completely replaces that abstract origin. Let's move to these visuals and see how this builds out. Notice the nested double helix rotations of that finite area D. On the left, we're seeing the state at n equals 4 rotations, and over on the right, it's n equals 8 rotations. What you're really looking at here is the slow physical contraction of the resolution unit. With each recursion, the central area D, that brown square you see right in the middle, decays. But, and this is absolutely vital, it remains a finite area end. It literally never reaches 0. The underlying structure of the math completely prevents it from just disappearing into a point. All right, part 4, grounding the silver ratio.
To truly appreciate how structurally sound this all is, we need to unpack the mathematical constants making this finite decay rate possible. If we look at the data from these halting examples, we see exactly how the area decays over time. At 4 rotations, the decay rate is about 15.9% per recursion, leaving exactly 50% of the area remaining. Jump to 8 rotations, and the decay rate drops to roughly 8.3%, but again, maintaining 50% of the area. The really crucial takeaway here is that the decay percentage shrinks with every step. It gracefully slows down so that it preserves a physical remainder. It just never bottoms out at 0.
And this controlled decay leads to an incredibly elegant alignment, which we can see right here in the symmetric diamond tile spiral. Because we're using discrete tiles instead of a Cartesian ghost grid, we can actually address surface regions using a global sequential count, which is represented by the letter Z. When we map this out, something amazing happens. The perfect squares of that count, Z squared, land with bit-perfect alignment precisely on the cardinal horizon. You can see this highlighted as the white tiles on the vertical and horizontal axes. The geometry just naturally, inevitably organizes itself.
So the crucial point is why this precise arrangement works so well, and the answer is the Silver ratio. With the scaling constant d equal to the square root of 2 minus 1, it acts as the ultimate structural stabilizer for this entire manifold. First, it provides that physical boundary for state secural, basically our squirrel's quirk. Second, unlike other metallic means, it decays slowly enough to actually be used in classical surface design architecture. Third, it's tied directly to that fundamental a squared plus b squared equals c squared base scale. And finally, it guarantees that internal finite d, ensuring we always have an area end rather than an endless void. We can see this stabilizing effect perfectly in the Turing cell neurology right here. The unit constant, d0, is dynamically built from these discrete sublenses. It establishes a self-similar, finite boundary dictated entirely by the Silver ratio, and that results in these really beautiful octagonal boundary conditions. It's a closed, complete, and highly robust system that just doesn't need to rely on the crutch of infinity to function.
And finally, Section 5, halting the infinite loop. Tying all of these geometric mechanics back to the real-world meaning of halting Turing's problem, we are looking at a massive paradigm shift. This framework entirely replaces the vanishing point end of infinity with the remaining area end finitude. And this brilliantly illustrates how, by shifting our perspective from a legacy paradigm of line infinity to area infinity, the quirk gives us actual finite surface areas. We no longer have to worry about ghost grid vanishing points, endless irrational divisions, or that pesky Neperian drift. We have officially and geometrically halted the infinite loop. The authors of the Hawesietata Universali research really capture the potential of this breakthrough beautifully in a letter titled Usufruct Ends. They write, and I quote, "If this is the nut, the compression, then what comes next must be the slow, recursive unfurling, the acorn, the sprout, the branching structure of instanced meanings." It's such a great thought. Once you fix the foundation, once you establish a solid, finite area to build upon instead of a bottomless pit, the potential for growth and mathematically stable complexity is completely boundless. Which leaves us with a massive paradigm-shifting thought to end on today. If Descartes' continuous point set manifold inadvertently created bugs like Zeno's paradox by just assuming infinite division, what else might we be wrong about? Seriously, what other assumed infinities in our universe, in quantum physics, or in theoretical computer science are just waiting for a mathematical quirk? If reality is actually built on discrete tiles rather than an infinite ghost grid, the universe might be a lot more grounded and a lot more measurable than we ever imagined. Think about that the next time you try to wrap your head around infinity. Thanks for joining me on this explainer, and I'll catch you next time.